Welcome to Ask and Learn.
In this problem, we have a conditionally convergent series, and R is any real number. Now, we'd like to show that we can rearrange the sequence AN. So let's say right now we have something like this, and then now we're going to rearrange that into a new sequence here. So where these B's are equal to the J's, but the order is changed. So for example, you can say something like we'd have something like of that form. Or more generally, even or here, sigma is a one-to-one function. Okay, so let's make some observations here. So conditionally convergent implies convergent. And this will imply, if we go to the divergence test, that if you take a limit of the ANs, those have to be 0. Now also, let's look back to exercise 51, where we find additional sequences. Positive part of AN, also the negative part of AN. And notice that since this limit goes to 0, that would imply that both of these limits also have to go to 0. Because as n goes to infinity, AN goes to 0, so these guys vanish, but so do these. And one more remark from number 51. If you go to part B of that problem, and assuming that the original is conditionally convergent, we could conclude that the positive part diverges to infinity, and that the negative part diverges to minus infinity. Okay, let's go on to the next page here. So now the next step is to rearrange the AN. So we'll go ahead and call this new arrangement, this rearrangement BN. So here's how we'll do so. So if we have the following, it takes sums of these BN terms, any BNs you want, any of the ANs, I mean, and if you include one more term, let's call this BK, then we can include that this BN plus 1 had to be negative. And we could even go a step further. Now let me go ahead and verify, prove this last case. So we have 1 to n BK bigger than R. And then let's go ahead and add the negative sum from 1 to n plus 1 of the BNs on both sides. And now since Bn plus 1 is a negative number, this is a positive number. And so that's why we can just denote this by Bn plus 1. So here, in this case, we want to know how should we choose Bn plus 1. Well, we see that it has to be a negative number because of this. So that can help us here. So we'll go ahead and take bn plus 1 to be the smallest remaining term in the sequence of negative terms. And as we noticed already, that as this is an increasing, so we could rearrange these in increasing order. And as we observed on the last page, these go to 0. And this is useful here because if we look at this term right here, we just showed that the upper bound is going to 0 in this case. And it looks like that will imply that this partial sum is converging to R. But in order to conclude that, we'll look at another case similar to this first one here. So let's go on to the next page. So this is the other case where you sum n of the b's and you get less than R, but then you include one more term, and it's bigger than R. So in here, this must mean that bn plus 1 is positive, and it also means this is a positive number because of this. So if you want, you could even put absolute values there, but it's not necessary. This will be less than bn plus 1. Again, I don't need the absolute value because it's positive. But as we noticed on the last page, we should mention how to define bn plus 1. And this time we'll take it to be the largest remaining term of the sequence of positive parts. And this is now because we ordered this in decreasing order, so they're getting smaller each time. So by the divergence test, as we noticed on the first page, this will go to 0. So what we just showed is the following. Regardless of which case we're in, either case 1 on the previous page or case 2, we just showed that this number can always be set less than some number that tends to 0. So I get more formally, let me write this on the next page. Given any positive number epsilon bigger than 0, since our sequence is converging to 0, we have, let me take a step back here. There exists, sorry about this. By the way we chose the b's in each case, they have to get smaller and smaller. So eventually we can make it less than any epsilon. But also taking n larger than the same n here by our previous work shows this. That the error between the actual sum R and the partial sum less than bn plus 1, but that's already less than epsilon. So therefore, we just proved that the sum converges to R, and that resolves the problem.